So in this lesson I want to look at another example of showing simple harmonic motion. Slightly more complicated question than before, in that we're given a position function where it's the sum of a pair of trigonometric functions. Before, we've looked at an example where we just had something like the position is given by b sine omega t. Here we're given a sum of a cosine omega t plus b sine omega t. And I'm going to break this video up into two parts. So I'll do first of all, I'm going to answer the first bit, which says prove that if the position function of a particle at a time t is given by x equals a cosine omega t plus b sine omega t, then the particle moves with simple harmonic motion. Okay? That's what I'm going to do. First of all, I'm going to just prove the particle moves with simple harmonic motion, and then I'll do a second video on finding the amplitude. And the amplitude it's telling me is square root of a squared plus b squared, so we're just going to prove that in the second video. So the first thing is to prove it moves with simple harmonic motion. The big thing is to understand the definition. An object's moving with simple harmonic motion if and only if its acceleration is proportional to its position relative to a fixed point, but is in the opposite direction, so it'll have the opposite sign. So that's what we're going to do. So ultimately, to prove simple harmonic motion, we do this. We take the position function, we differentiate twice. First derivative is the velocity function, second derivative is the acceleration function, and then we show that that acceleration function is some negative constant multiplied by the position function. So what I'm trying to show is that my acceleration is going to be a negative constant multiplied by the position function here. In this case it's x. That could be given as x for position or s for displacement. The derivative of position is velocity, the derivative of displacement is velocity. In this case it says it's the position function. The second derivative is acceleration. So all I'm going to do is I'm going to twice differentiate and find an expression for acceleration. That expression, if it's a negative constant times x, well then we can say it's moving with simple harmonic motion. So I might start off by saying that simple harmonic motion, if and only if the acceleration is equal to some negative constant multiplied by x. That's ultimately what I'm trying to prove. So I'll start off by saying that. The next thing is just to twice differentiate. So I have x equals a cosine omega t plus b sine omega t. So I'm going to twice differentiate, and at this stage I'm going to go quite quickly through the differentiation because we've done a good bit at this stage, and hopefully you're able to do this pretty well. So velocity is just the derivative of displacement or position. So velocity here, first of all, is a cosine function, so the derivative of cosine is going to be negative. Also, I'm factoring out the a. Also, we're going to be using the chain rule. The derivative of cosine of the argument is negative sine of the argument times the derivative of the argument. The derivative of the argument, omega t here, the derivative of that is just going to be omega, and then we're multiplying by sine of omega t. Okay, similarly, the derivative of sine is cosine, and you'll be using the chain rule because that's omega times t, and what you should get is b omega cosine of omega t. So that's the velocity function. I'm going to differentiate one more time to find the acceleration function. So again, differentiating, derivative of the sine function is cosine function, but I have to use the chain rule. Multiplying this by omega, I'm going to get negative a omega squared. Similarly, taking the derivative of cosine, that's going to change the sign to a negative. Using the chain rule, I'm going to get sine of the argument times the derivative of the argument, which will be omega. Omega times b omega is going to be b omega squared. Okay, so differentiating those two things you should be able to do pretty efficiently at this stage. The other thing I'm going to just now is try to express this acceleration as a negative constant times the position function. So I'm going to factor out a negative omega squared And when I factor out a negative omega squared, it's multiplying by a cosine omega t plus b sine omega t, and that quantity inside the square brackets there is exactly what x is, so which is equal to negative omega squared x. Okay, so that's it. That's pretty much it. So conclusion, therefore we have simple harmonic motion since the acceleration is equal to a negative constant times x. Okay, that's what was asked. A couple of things just to note. I haven't asked this in the question, but just to note, omega is a quantity inside here. Remember, we said that we can work out the period. Once I find out what omega is, we know the period is always going to be 2 pi over the absolute value of omega. Okay, so we know that the period is going to be equal to that, so we can find out the period of this function. We also know that the frequency is the reciprocal of the period, so the frequency would be the absolute value of omega over 2 pi. So we can calculate these things once we know what omega is in this case. Okay, so that's the first part of this lesson, which is to prove it moves with simple harmonic motion. In my next video, I'm going to look at the same question, and I'm just going to explain why the amplitude of a function of this type will always equal to square root of a squared plus b squared.